Welcome to today's webinar, Tool-Based Structural Design Optimization in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, the German and English webinars, customer projects, etc. I will be the moderator today. My two colleagues will support me, or Andreas Niemeyer will do the presentation and Frank Faustich will support me by answering the questions, but they can introduce themselves.
Hello, I'm Andreas Niemeyer and I'm responsible for the product engineering here by Dlubal, and today I show you this webinar.
Hello, my name is Frank Faustich. I'm responsible for quality management, and today I will help to answer the questions.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can hide or show it with that arrow here, and then enter your question here and we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and email questions to info@dlubal.com. Okay, then I hand over the screen to Andreas that he can start with the presentation.
Okay, thank you, Andreas. Then I take over with the topic tool-based structural design optimization in RFEM 6. Before we start with this interesting topic, I want to lead you through these main points of this presentation, and here I defined 4 points. In the beginning, I want to describe the function of the structural system itself, so how it works together, what are the nonlinearities, and so on. And then we transform this model with an idea of optimization into RFEM. Finally, of course, we evaluate the results, and at last but not least, I repeat all functions and all features what are existing right now and give an outlook to this technology. On the right side of this slide, you can see 3 pictures. Maybe the most interesting one is the upper right picture, where you can see a column foundation. It's a wireframe model, and this is maybe the main focus of today, where we show how you can optimize a horizontal loaded restrained column and how big the foundation plate have to be for a specific load. This example we check manually, we optimize manually, we will optimize by an add-on, and at last in the last sequence we also try different foundation shapes to see what is the best solution. So now we can jump directly in the program because we do it live. So I close this presentation. And we open RFEM. For showing you how we can calculate the column foundation, I open a new model, maybe with the name 0D and O for online, and open a new sheet. So for all this work, we use our general RFEM environment, and we start by modeling the column member by changing this working plane into XC and using this member command to define a beam member and define here a cross section. I use here a massive square section where I define here the size of 300 millimeters, and I define here a material, let's say standard concrete, for example, this one. So now we can place the column in the space, and we know we assume for this example, the column should have a height of 3 meters because maybe architectural reasons. And now we model the second part of this structure, and for this we change this working plane into XC, and now we model this foundation plate, and for this foundation plate I use a command here, rectangle via center, because with this command I can show you exactly what is our work for today. And we select here the thickness. Maybe I write now, or I use the standard input because I don't know what the right thickness is. I know, for example, which material we need, but the thickness itself is at the moment a question mark, and I use the standard setting from the program. Now we can place this foundation plate in space, and of course we know the center is here in the middle of the column or on the leg of the column, and this graphical appearance of this command is pretty good to explain, because we can make now a square shaped foundation, we can make a rectangular shaped foundation with an orientation in X, we can do it the same in Y direction, we can make a big square, whatever. We don't know it right now if we have to design something like this. So I pick the grid points to reach a size of 2 by 2 meters. These 2 by 2 meters we can also dimension here, that we always have an overview about the global size of this structure. Then what we know for such structure types is maybe the load, what they should overtake. In this case, we know the surf weight have to be overtaken. The surf weight is calculated according to the column size and length and the size of the foundation plate. What is open and can be bigger or smaller, the analysis will show. So surf weight is clear, plus, let's say, a horizontal force. For this example, I take it into X direction, but it can act also in other directions. So here we define, for example, 20 kilonewtons, and I place this force on the top. We have now here one load case. For analysis reasons that I can show all functions, I decide now that we work only with this load case, that we have only this self-weight load case with activated self-weight according linear analysis with this 20 kilonewtons horizontal force. Now that the calculation is startable, we need a support. This means the force of 20 kilonewtons should run through the column into the slab and should be taken over from the soil. So we need a surface support here, and I open here the properties and activate the support. And the support is here. I simplified a little bit. I assume that the horizontal forces will be taken over from the refill surface, and the vertical part should taken over from vertical spring, soil spring, and I use here, for example, 100,000 kilonewton per cubic meter. Now, we have a model where we can start calculating to see what happens. Let's repeat. We used a standard thickness, and we used also a standard width for the soil slab. And now, when we give the program the command to calculate the equilibrium, it will mesh the structure, and it will give us finally deflections and forces. We see here we get a deflection of 12 millimeters. To show it a little bit better, I use this wireframe model, and you see we have here deflection, and this means we have here a shear force of 20 kilonewtons. We have following a bending moment, 60 kilonewton meters on the leg here, and this bending moment will be run into the surface, into also bending moment, and finally the soil take over these forces into a contact stress in sigma c. And to see it better, I hide this surface support, tabs for surfaces, and you see it quite obviously that we have here on the right side a positive pressure downwards, and on the left side a negative suction upwards. What is so far clear, and you saw also that the program gave us an equilibrium. But when we think about these results, we will realize how could it be that the foundation use here a negative stress upwards. It seems like the foundation is glued to the bottom, and this is not real, I would say, because I cannot glue a concrete slab to the soil. It can only work by pressure. So I have to give the program the information to simulate this effect. And we can simulate this effect by changing the type for surface, this supports. Maybe clean up this list here. Now we see our support definition, what we defined, and I define here a nonlinearity failure if negative contact stress. This means if the contact stress is downwards in C direction, it should act, and if it goes upwards, it should fail. So I select, this function. And if I run this analysis again, we will suffer a problem that we get an instability. You see, program don't find the equilibrium. We get a deflection, a really huge deflection. And when we check the, let's say, deflection shape from the last situation, you see we have here uplifting situation. This slab or the full construction is not able to transport this bending moment down to the bottom because it's too slender. The weight is not enough. And now the question appears, what can we do? We can reduce the load, or we can modify the size of the slab. For today's session, I want to do both. Let's do the easier one at first. What means think about what we can do to get an equilibrium by changing the load. And if we want to do this, let's make a small sketch to think about what is needed. For this, I use my graphic program here and make a picture of this. And now I have the option to draw something. And here I want to draw, or what is also important, if we take a look on the static analysis, we see in the sum of loads that we have a horizontal component of 20 kilonewtons and a vertical component of 26.75 kilonewtons from self-weight. So this is pretty static when we don't change the model size. And this size we want to modify. What means I draw this arrow here and say, okay, here we have a vertical component would have a specific length, is 26.75 kilonewtons. But we have also this bending moment of 60 kilonewton meters, what maybe could be visualized as a pair of forces. What means I have here a pair of forces in this direction. And you see, this force could be taken from the support springs, but this force should be taken from the self-weight vector. And if this vector is longer than this vector, I have no chance to get an equilibrium. So my task is to find a way to elongate this force minimum this purple length. And how I can do this? If I play with this cantilever or lever arm in between. For this, I draw here a small lever arm in between to get a better view. I change it here like this. And now the question is, how big have to be this? Or this is also not how big, because this is already clear according to the size of the foundation, but it depends how big this bending moment should be to be in equilibrium with this purple arrow. And for this, let's describe here a small formulation. I use here maybe a text box to write the main formulas down. And at first you have to know this length here. We know from our system here that we have 2 meters and half of it is 1 meter. And this is almost an assumption to take, but I want to take it more in detail. What means when we take a look on the top view, you see the program meshes this slab into a few elements, and I defined every element have a length of 0.5 meters. And in this case, because we're working with finite elements, we have to know that I can always have full length of elements, and here on the lateral side I have to go to the integration points. So I have not completely 1 meter and a little bit less, and this I copy now below our sketch. I insert it here, and let's say I reduce the size a little bit that we have an idea about, and now we can draw this lever what we need for investigation. It's not completely here on the edge, then up to the integration points, a little bit smaller. And this I want to formulate now here in our box. We know the lever is, let's say, for the first element here is 0.5 meters. And we have a second element with 0.5 meters. So again, 0.5 meters, but this we have to reduce a little bit. We need a half plus the distance of the integration point 0.289. And this results into a cantilever of 0.894. Pretty certain, but I need this accuracy for giving you an idea about the reaction of this model. So now we know exactly this purple length. It's 26.75 kilonewtons, and we know this green length of arrow or lever. And according to the conditions that the bending moment what acting here on the bottom divided by the vertical force is the cantilever, we can write, let's say, a formulation of 0.894 meters. And this we write more detailed, what means this M is maybe a horizontal force, so F multiplied with 3 meter length divided by the vertical component of 26.75 kilonewtons. And if I calculate now the F, I receive 7.97 kilonewtons. And of course, this we have to check, I would say. And we try this now and change our force here to 7.9. Let's take 7.9 and run again an analysis. And you see the program will find an equilibrium. The deflection is okay. And we get finally also a contact stress on the bottom, and everything is fine. But if we increase the load a little bit, we will see we get again an instability, what proves our calculation at least. So this was a first optimization. What we can do, we can modify the load to get a working model. But the reality is a little bit different. We cannot say the force is much smaller, then we have to accept it in almost all cases, and we have to find a model what fits. This means go back to 20 kilonewtons. We only learned that the size of model is, or the working model is connected to the horizontal force. Now, what we can do if we should take over this horizontal force with this structure, we only can modify the size of foundation plate. And because we don't know what is good or which size is good, we try to optimize the structure at first manually. For me, I select these nodes. I do these changes always symmetrically because I assume the force can appear in both directions. So I increase it by double by 4 to 2 meters and start a calculation. And what happens, or what is expected? Yes, of course, now it's working. So for me, it means, okay, I can go ahead with my work, but I have a bad conscience, because what is when the size is not 4 meters and 3 meters? I can save a lot of concrete for this. So let's try. So we take these nodes, go into the properties and try a further solution with 1.5, and the same on the other side. 1.5, edit, minus 1.5, and run again. And we will see that this solution is not working. This says to me now, okay, 4 meter was working, 1.5 not, so I have to increase it a little bit. So I go again into this middle, I optimize this structure. So let's move these nodes again. Try here now, for example, 1.7 meters. And on the other side also, nodes, edit, minus 1.7, and run the next analysis, and you will see it's working, I hope. Yes, we get a solution with 3.4 meters, everything is fine. This says to me 1.5, so 3 meters was not working, 3.4 meters was working. Let's try to make it a little bit smaller and check if it's fine or not. And if we reduce it by 20 centimeters, so we write here now 1.6 on the right and minus 1.6 on the left side with 3.2 meters. And if we check it, we will see, you see it here in this diagram, if it's getting a big deflection, it's not working. This means for me now, this 3.2 meters is not enough. I have to increase it to 3.4, and everything is good. This was now a manual optimization, what we did. I think you know it, and I know it also from our support work. When we try to get a model what fits, we play with these parameters, what is quite boring work and time exhausting. And even if we read now what we reached now a foundation size of, let's say, 4 tons roundabout. We cannot be sure if this is a good optimization, because we changed only this parameter in X direction. We don't change this parameter in Y direction and the thickness parameter. And if we imagine we have to create hundreds of such foundation situations, it could be interesting how much concrete you want to use for this stuff. And therefore, we set up this demo today to show you how you can use optimization in RFEM. And now I end up with the first point to show you what is a model, what could be optimized. And now we transform this optimization task into RFEM. What means we have to learn RFEM, what he can change. For this, we go into the global parameter list. I open here below menu edit the global parameter list and set up, let's say, 3 parameters. Bx for the length in x direction. It defines 3.4 meters, for example. It's a length parameter and it has a value type. And we have a parameter by for the dimension in the other direction. Let's define here 2 meters and a thickness parameter for the thickness of the surface with 0.2, for example. And now we take these parameters and memorize it into the structure. For this, I select the right 2 nodes, go into the properties and open here the formula, edit, and write bx divided by 2. Nothing changed because dimension remains the same. Now on the left side, nodes, edit, here formula edit minus bx divided by 2. Pretty easy. Now on the other direction, select here, nodes, edit. Now we use the y coordinate minus by divided by 2. And now the last node set, node edit, by divided by 2. Now we made the horizontal distances in x and y according to the parameters, and the last one, the thickness parameter, only that you see also another input method. I go into the table structures, basic objects and thicknesses, and here we have our 200 millimeters written. I can write here also is D, and the program accepts it. And if you want to see these parameters, you can change here the view, and you see we have here D, and in the node table we have our bx divided by 2 and so on. So you can change here and you can write it also in this style if you want. It's open. Now let's try if it's working. If I change here a parameter to maybe 4 meter, the program changes the dimensions to 4 meter. So this shows me the program can now or knows now what he can change with these parameters. And at this point, we go back to the base data and activate an optimization add-on, an optimization and cost CO2 emission estimation add-on. Pretty long name, but it's hidden a lot of features behind. And for this, I activate it and I jump directly into our parameter list back. And maybe you see the change. You have now here optimization columns. And this allows us to say, let's optimize, for example, this bx parameter with a new definition tab. Now we have here optimization, optimization ascending, descending. This is important to describe the, so optimization is a general definition, and here you can additionally describe if you increase the value, it have a good property for reaching the optimization goal. For example, if we want to have a minimum weight, it's good if we reduce this figure because then it's going smaller. That we learn this program, this information in begin, we can use descending here. In our case, we use the simple input, let's say optimization, and describe the program, what are my input steps. And I say him, maybe start from 1 meter and go maximal to 4 meters with a step of 1 meter. Ah, it's too big, 0.25. So now it's absolutely clear for the optimization tool in background, which steps he have, what is the minimum, maximum. And if we confirm this setting and open below the menu, calculate the optimization settings, you will see the program mentions this bx parameter for the optimization, mentions here at the bottom what are our possible structure mutations. So we have 13 different structural appearances, let's say, and we can activate it here for calculating. So if I have this check and press here this option, he will optimize. And the program maybe when he calculates the 13 solutions, he asked me how much solutions I want to document in my model itself. And I say, in this case, okay, document everything. It's not too much. 13 is okay. Now the question appears, when we optimize, what is our optimization goal? And the goal or target is here to define. We can define minimum total weight, a minimum vectorial displacement, member deformation, surface deformation, minimum cost, CO2 emissions, or referring to a user-defined parameter. We use the easiest one, total weight, and optimizer, we use all mutations. What means it's not an optimization, then it's a run through every solution. And this is now the point where we say, okay, let's start and see. And what happens now? The program opens an optimization process in the calculation. He writes down at which mutation he just working. And you see the program is changing the structure during the optimization process. So he shows all mutations, and he have here a table optimizations where he logs working mutations. And at the moment he logging nothing because we realized in our test before that these small foundations leads to an unstable system. So he only logging systems what are working. So I'm also under tension was which solution will work, but let's see. What for me is important now, if you count the amount of seconds, how long we need here. And if we now start with 1, 2, 3, 4, 5, 6, 7, maybe 6, 7. So let's say 6 seconds or 5 seconds to be optimistic. We have to scale it up. So for 13 mutations, we have to multiply it with 5 seconds. We need up to, let's say, a minute, yeah, or a little bit longer. But it should give you a feeling what happens if we give the program the job to calculate 13 mutations. He needs the time to calculate 13 mutations. I say in the moment, let's say 5 seconds leads to a reference time amount of 1 minute. Now he's finished, and he gives us an optimization list of 3 mutations. The 11th leads to a good result to 4.18 tons weight complete with a foundation size of 3.5 meters by 2 meters with a thickness of 20 centimeters. Yeah? Nice. Can we go ahead now? Can we say now we order 100 of these constructions because this is a really efficient weight? We don't know, because we don't optimize according to the thickness, and we don't took care about the width in y direction. We cannot say exactly. So I want to say, let's try to say now, we optimize also the thickness, for example. So let's give the program the job to optimize the thickness and start here from 0.2, go maximum to 1 meter, and increase the steps with 0.1 meter. So far, pretty easy, but if we take a look into our optimization settings, we get now also the D parameter here, that is fine, but this figure increased enormously. So now we have to deal with 117 mutations. And if we scale up this with our 5 seconds, we end with 10 minutes. So not only once, and we increase the time by 10, only by feeding this additional parameter. Of course, we can use this optimizer all mutations for this, and I did it also for you. So I open this file here, 2D, to give you an idea how it's looking like. And you will see that we can decrease the weight of the foundation pretty much by optimization. He found a solution with 3.5 tons by using a size of 3.75 meters with a thickness of 30 centimeters. So there is some potential to decrease the amounts. Yeah. The question is only how much time you want to invest. And now imagine we can extend this question more when we say, let's optimize also this parameter or this width in Y direction. So I close this and I prepared also a file to show you also this solution. Open 3D. So this means not 3 dimensions of space. This means 3 dimensions of optimization. So in Bx, By, and thickness. And now if we open this list optimization, you see we could decrease also the weight of the foundation more from 3.5 tons to 3.18 tons by using a dimension of 4 to 1.25 and 20 centimeters. So everything is possible. It's your game. The question is only if I took now a look into our optimization settings, we have to deal now with 1,500 mutations, and this leads to a time of 2.1 hours now. So I would say 2.1 hours. I would accept it. I can drink a lot of coffee during this time, but slowly we should think about how we can improve this situation. And for this, I want to show you our further optimizer, particle swarm optimization. And we use it for a simple example to explain everything. So I close this stuff here and open our initial model where we have defined already the parameters. So we have here activated the optimization for the Bx and the optimization for the D parameter. We can also say maybe start here with 1 meter. And here we place the starting value in the middle of our ranges. So we have here 3.5 is fine. And for the thickness, we use 0.6. because we don't know it, what is the best solution. And now, if we go in our optimization settings, you will see our 117 solutions, what means generally 10 minutes calculation time if I optimize it according all mutations. But I can use here this particle swarm algorithm. What is a self-learning algorithm? And you have here to define a second input, what means a number of random mutations. This means if I define here 20%, that the program gets the job to calculate within 20% of this 117 solutions. What is, let's say, I think 22 mutations, a pretty good solution to be close on this optimization target. How can this work? So I say please document 22 mutations because this is what he calculates. And 22 solutions means not 10 minutes and less, because only 22 multiplied with 5 seconds. And if we start this process now, the program starting with this self-learning process, placing parameter sets by bx and b and thickness, and learning from the reaction of the calculation how he should change the parameters to reach a result. How is this working? I want to explain it to you. And this particular swarm algorithm is could be connected or simulates an animal swarm, maybe from fishes or birds or whatever. And every individuum of this swarm could be compared to a parameter set. So this 4 and 0.3 is maybe one individuum of this swarm. And we know when we watch these swarms in nature, we see every individuum of such a swarm have a minimum distance. And when you watch it over time, you realize they have a need to find a resting place. And as closer they are coming to the resting place, the need will be increased. And this behavior is used in this mathematics behind. So as closer we coming to the optimum, as more they will find it. And this is pressed into an algorithm. And to explain it in detail how it's working, I use my graphic program here. And I extend my picture, maybe here in the right side, and make it here white, and draw a coordinate system. So a coordinate system, quite easy. It should show you the result space. So we just learned that we have, or not learned, we specified for this algorithm process that we optimize this bx parameter, and we optimize here the d parameter, the thickness parameter. So, and this algorithm starts now with a random result set in this result space, in this possible result space. And I want to visualize it here with such a star icon. So let's say he takes for the first star 2 random values, what are placed here, and we, let's say it's only expectation, but after calculation, and now I would say my expected optimum result is lying here. Yeah. Now, and when the program is starting with this particular swarm algorithm, it decides randomly for a specific amount of values in this result space. Maybe here bx is 4 and 1d, and here we have 1bx and 4d. So it means explicit values, and it giving them result sets also an inertia and a traveling speed vector. And this traveling speed vector is running, for example, in this situation, it's random selected here in this direction and here in this direction. And this means for this is first iteration, for the second iteration, when the program is calculating this new decided result set, it realizes that this value, let's say this value, it's one, this result set is running and knows this was my personal best solution. So make it yellow. And this set knows, no, for the second iteration, this is my personal best solution, because here I'm closer to the target and here I'm away, so this is closer to the target. And now knows it also because it travels here, this seems to be the global optimum value, so I write it in red. Now in the third iteration, it finds a vector, a new traveling speed vector, what is according its personal best value and the global best value, what means we're going in resultant direction between these both. And here we know, okay, our global best value and personal best value was in this direction. We travel in this direction because we think it's good. What happens when we investigate these new results? We see the personal best value of this run is now changed from here to here because we are closer to the target. So it's yellow and this will be blue. And here we see this will be the personal best value because this is more far away from results than this. So this remains by blue, but it's only a personal best value, and this will be the global best value. And you see now in the next iteration, we're going in the direction of its personal best value. So we're going in this direction. We don't meet exactly this place. Because he don't know where the optimum is, but he know I'm on the right path. And here, for this direction, we take a new vector for personal best value and global best value. We go into this direction. And you see, with this algorithm, we come in pretty close to the global optimum. Of course, we don't meet it, but we have a chance to calculate within less iterations pretty close to the optimum. And now we see, if we take a look on our 117 possible mutation calculation where we checked only 22 solutions, we found a pretty good value with calculating only 22 solutions or mutations and not 117, what means a time save of more than 50%. Yeah? And this is really interesting as more parameters you have, and gives you the option to investigate this type of models really in detail for this topic. Now, as we learn now how we can deal with these different parameters and that we can extend it, I want to open the next question. So we took a look on the optimization of BX parameter, BY parameter, thickness parameter, but we should be open-minded, and I want to give an idea what is if we have a circular foundation shape, what is if we have a triangular foundation shape or a square foundation shape or trapezoidal foundation shape, or we use different materials. Everything is possible. We can give the program the job to find the best solution within less iterations. And I prepared this idea of different foundation shapes for this webinar, and I coded here a small script. It's not complex. I think it could be done from everybody. It's not really long. It have 130 lines. The content we go through a little bit later. It's only a file right now, but we can use this model here and say save as block, and write here, for example, webinar opti. Then we can give descriptions. The save as block takes a picture of this current model. We can give a category. So you see we have here beams, trusses, frames, spheres, so all categories of Dlubal Center. For our presentation, I use here other. We can also give a second category to find it better in future. And here on bottom, we have the option to connect to a script file. So I connect here to the script file version 4 with English comments. And if we confirm this, the program is taking over this script into the program environment. And now when let's delete this model. When we go into the block manager, we will see the Dlubal Center with the block manager, with these categories, beams, trusses, frames, spheres, and so on. And here we have other, of course, you see I trained a little bit, but we have here our webinar Opti. And I take over this model. And yes, it changed already. We have here triangular shape. But to explain this, we jump now into the structure input. Here you see I can specify the size of this model by a few parameters, and surprise, it's the same parameters what I used before. So I can select here maybe the BXY length, the BY length, the thickness, and I have a new parameter, a shape parameter, what is maybe 1 for triangular shape, 2 for trapezoidal shape, and 3 for square shape or rectangular shape. So I can control this structure by a few parameters, not only by dimensions, and also I can control the model itself and the amount of elements with a parameter. I can assign here foundation support, loading, everything is defined so far. And we have in a search register here the categories, and finally even this JavaScript code what I connected to this block. And now we can go through, and in the first part what is important to understand, we have a function input data, what is running from here to here. And if you read it, you see I open a category geometry, foundation with BX, foundation with Y, foundation thickness, shape, supports, loading, and so on. And if you compare it to the structure input, you will realize I can program with this script this tree of inputs. It's in your hands now. You can write by code an input scheme directly. Further, you have a second block, a generate block, what is running now from here to bottom. And the generate block generates now structure in our program. Here the height of the column is defined, and I define the material, I define the thickness. Now I define the, let's say, surface according the shape setting. 1 is triangular shape, I define 3 nodes, 3 lines, a surface by these 3 lines. 2 is trapezoidal, I define 4 nodes where I spread maybe BY and BX with a factor, 4 lines and surface. It's the same for the rectangular. And after the shape or the surface is constructed, I assign the surface support, I define a cross section, I define nodes for the column 5 and 6, I define a column member between these nodes, and finally I assign a load case with maybe the parameter force. What is defined here, force 20 kilonewtons. So it's pretty easy, I would say. I'm no programmer, I'm an engineer, but I was able to do this, so I think also you and programmers also. And now let's connect it to our idea of optimization. We have here our input. So if we insert this structure into our model, you will see we have it in our model. And if I draw with my mouse above, you see it's one block. I can change it afterwards. So I can go into special object blocks, webinar Opti, and see here BX is maybe 3 or 4 meters. Then I confirm it and I get a changed structure. And this connection I can connect to our global parameters. What means? When I say this value should be optimized, this value should be optimized from 1 to 4 with a step of 0.25, and we have also a form parameter. And this is now no length, and this is a integer value of model. So we have defined here as integer. I can say it's a value 2, for example, and it should be optimized from 1 to 3 with a step of 1. Okay. I can use these parameters in our block by say this is bx, this is by, this is d, and this is what. And you see, we can now control this block by using this global parameter. So if I change the shape, I get the rectangular shape. Now the game is open for optimization because the program is not interested in what you optimize. It only optimizes parameters and learns about the finite element program information back to decide what is a good and a bad information. So if we see here optimization settings, we have all 3. And what is really interesting, we have now 4,500 mutations. And this figure, if we scale it up with our 5 seconds, we speak about 6.34 hours. I know because I did the calculation last Saturday and the computer was running and running and running. And I was really interested what happens if this shape of foundation is really important in this idea. And I can open this model, and therefore we have 4D because we optimize 4 dimensions of values, so bx, by, d, and shape. And as you can see, our rectangular assumption is one of the best solutions, but the other shapes are also not close or not far away from the best solution. So I go to my optimization table, and you see the best solution was with 3.18 tons, rectangular shape, 4 by 1.25 meter with a thickness of 20 centimeters, shape 3. But you see here we have shape 2 for the 7th place of optimization, shape 1, 2, 1. So it was a mixture. And when you optimize, you should be open-minded and should think about what I can change. The computer can do the work for you, and you let him calculate. And this particular swarm algorithm helps you to save time. Yeah. And now I'm coming with this to the end of my 3rd part and want to close this full demo with the status quo and outlook. And for this, I repeat again what is possible now. At the moment, it's possible to give the programmer optimization jobs for any number of parameters. So you can extend the list as you want. There is no restrictions. It's only a matter of time. Further, it's possible to place these optimization parameters in the topology inputs, but also in these, let's say, intelligent blocks data, what can base on any script inputs. And the script inputs helps you to create structure as you want. Yeah, you can decide if the length is 4 meters, I need 2 supports. If it's 8 meters, I need 3 supports. Whatever, it's up to you. You can program everything, and you can connect these input parameters to these nested tables. What is really a big feature for this technology. Then you can you have different optimization targets. We took a look on this today. You can optimize according weight, vectorial displacement, member deformation, surface deformation, minimum costs. So you can define in in the material settings that the cubic meter or square meter of this material costs something like this, and then it will be summed up for this analysis. You can do the same for CO2 emissions, or what is really new, you can connect it to a user-defined parameter. Imagine you do a photovoltaic system and your main focus is the a kilowatt peak definition about what is connected to a surface of structure. So you can connect it to user-defined parameters. And further, you can do this not only for one load case. I did this only for presentation. The program checking all load cases what are available for this. So this means we cannot do it only for uniaxial bending. It's completely uninteresting for the program if it's here, if you have here 3D loading or whatever, and how much. All load situations will be checked. Further, you can use this not only for load cases and also for all activated designs. So if you say I have to do here concrete design for this structure with reinforcement, then the program shows you only possible solutions if the design add-on gives green light, what means a utilization smaller one or equal one. Everything what is overutilized will be hidden here, similar like an instability. So you can use also the information of add-on for optimization. Stress strain, concrete, steel, timber, masonry, aluminum, steel joints, and so on. Yeah, steel joints I'm not clear, but this main element designs definitely. Then maybe later, what also will be asked, you can also optimize cross section. So if you optimize, if you give here optimization attribute, then the full cross section series, maybe all AGAs will be checked. It's like a parameter range then. And you can use this for models or for intelligent blocks or a mixture of both. It's your game. You can connect it like you need it. And now to the outlook of the program. The outlook is what we want to do. You see, we have now a result, this optimization table, and I used already for explaining you this result space. We want to extend this program with a more dimensional diagram output where you can see where you have good results, bad results, and so on, where you can compare. So we will extend it with a graphical output. Further, our next plan is, it's always a matter of time. Yeah, we speak about when we do all mutations about 6 hours, and it is only a small model. So it's always a matter of time. And we're just placing RFEM into the cloud. This means we can install RFEM on a cloud computer where we can decide how much power we want to use or you want to use for your analysis. And this opens, let's say, a really powerful machine where we can decrease the needed time for the calculations. So I think this will be the next big feature for this analysis, to use cloud computers, supercomputers to reduce calculation time. Next, we want to open the field for checking or making optimizations for reinforcement in concrete elements, to play with the amount of rebars and sizes of rebars. This is also under focus. And if you see this criteria, optimization targets, here in this list we have weight and displacement and so on. But what means this? If I define here total weight, the program knows I need slender cross sections to have less weight, and he only searches for shapes what fits. But at the same time, the deflection increases because my cross sections are slender. When I do it vice versa, when I use vectorial displacement, the program tries to have slender cross sections, big cross sections, massive cross sections, to have small deflections, but at the same time the weight increases. So we should try, or we want to try to have a multi-criteria optimization where I can weight the different topics. And finally, if we say all these rows, what we have here during the optimizations is remembrances, or is a memory, and this memory will be stored here locally for this model. But imagine we extend it for in a global database that we store every remembrance in one big database. We can use it for the next analysis also and don't have to do it again. Because when I delete now mesh, everything is deleted and I have to do it again. But if it's stored globally, we can use it for this calculation and also for others. So there's a really big potential, and our team is open for all new features. Of course, behind every feature is a lot of work, but we like to do it. And I hope I could inspire you today with this webinar and give back to Andreas.
Okay, Andreas, thank you for this nice presentation. Yeah, we got a lot of positive comments. I think the attendees could see how powerful this add-on already is. And yeah, you gave us an outlook. Yeah, it's clear that we developed this add-on step by step. Yeah, you can try this add-on with the, for example, with the trial version. Let me share my screen again. The most of you know that you can download the free trial version here on our website, dlubal.com. For example, RFEM 6 and RSTAB 9. And yeah, we presented RFEM 6 today with the add-on optimization. And the trial version contains all add-ons, and you can use it for 90 days, and it's for free. And where you can find the recording and the model under news and events and webinars, you will find today's webinar, and it's here. In the next days, you will find the video here and here, and the model should be already uploaded. Yeah, you can find it here. Yeah, just try it with RFEM 6 if you have got already RFEM 6, but if not, you can use the trial version. Okay, that's also all from my side. Maybe a last comment when you leave the webinar, where's a small survey, only some questions. You can score us, and just note that the worst score is 1 and the best score is 5. You can enter wishes for future webinars. If not, you can enter a line or a minus or something like that. Okay, thank you for your attention. Thanks to Andreas for this nice presentation. Thanks to Frank for answering the question. I wish all a nice rest of the day. Bye-bye.